Hi guys, today we are going to talk about the history of imaginary and complex numbers. Imaginary and complex numbers were long looked upon with suspicion, and their possible existence was politely ignored. Cardano called negative numbers fictitious and elevated imaginary numbers to be sophistic. The Italian mathematician Raffaele Bombelli introduced imaginary and complex numbers in his treatise L'Algebra in 1572 in connection with the solving of cubic equations. Now let's get to an example by solving a quadratic equation. Our quadratic equation is x squared minus 4 times x plus 13 equals 0. If we try to find the discriminant of this equation, we get minus 36. So we have two different solutions. x1 and 2 are 4 plus or minus the square root of minus 36 over 2. And that gives the solutions 2 minus square root of minus 36 over 2 and 2 plus square root of minus 36 over 2. Okay, we suppose that the square root of minus 36 exists. So if we apply the formula, the factorization formula for the quadratic, this is the formula: a multiplied by x minus the first root and x minus the second root multiplied, we get ax squared plus bx plus c. And applying this formula, if we substitute these two roots here, we get x squared minus 4x plus 13. Supposing that the product of square root of minus 36 times the square root of minus 36 gives minus 36. So we can write down the square root of minus 36 equals square root of 36 times minus 1, and we break this square root of 36 times square root of minus 1, which is 6, square root of minus 1, which is 6i. I is the imaginary number, which is the square root of minus 1. So we come to our complex numbers, which are of the form z equals a plus bi. A and b are real numbers, and a is the real part and b is the imaginary part of this number. The idea of representing complex numbers with points in a coordinate plane originated with the English mathematician John Wallis in 1685. The first practical representation of complex numbers dates from 1797 by Caspar Wessel, and in 1806 in Geneva, Jean Robert Argand published anonymously in a small privately printed edition a method of representing imaginary numbers geometrically. So today we have our Argand diagram as you can see it here. And finally, the great German mathematician Carl Friedrich Gauss presented the complex numbers plane as we use it today. And before ending this video, I will show you how to represent a complex number in different ways. Let's say that we have a complex number z equals 3 plus I times square root of 3. So in Argand diagram, this is here, and this vector here represents the complex number. So this is 3, the abscissa, and square root of 3 is its ordinate. First of all, this angle here is the arc, the argument of the complex number, which can be found by inverse or tangent of square root of 3 over 3. that is pi by 6 or 30 degrees. We can also find the modulus of the complex number, which is the distance of this vector, the length of this vector, which is absolute value of z equals square root of 3 squared plus square root of 3 squared, using the Pythagorean theorem, which gives square root of 12. So I can also write the complex number in the form z equals square root of 12, this is its modulus, times a parenthesis cosine 30 plus I sine 30. So this is the trigonometric form of our complex number. So if you calculate all this, you will see that you will get to the result 3 plus I square root of 3. Another way to represent the complex number is the polar form. So the polar form is z equals the square root of 12, which is its modulus, its measure, times e to the power of I multiplied by pi by 6. This is the argument. Or another way to write it down, technically, you can find this in technical books, is the square root of 12, and here we put its angle, its argument, which is 30 degrees. Thank you for watching this video.